Okay. So our next speaker is Michel de Oliveira from the group, and he will talk about quantum advantage in temporary flat and utility.
Thank you. Hi, everyone. I'm going to present our work on the temporal structure of measurement-based quantum computation, which we have done with, in collaboration with Professor Ernesto Galvão and Professor Luís Jorge Barbosa at INL. And so, first I will go through the motivation that we had to understand the temporal structure of measurement-based quantum computation, and then more specifically the setting that we studied, which is the non-adaptive case, the one without a temporal structure. And then we used this model to study how we can compute decision problems, and if we need a temporal structure to compute decision problems, and then also show the circuits that we could build in this model. So our main motivation in quantum computation is to find quantum advantage. And so that means that given the quantum Turing machine, we believe that there are problems that we can solve with an exponential advantage. And that more technically means that the class PQP is bigger than the class P. So the class of problems that we can solve with the quantum Turing machine is bigger than the one that we can solve with the classical machine efficiently. And so one question is, and one motivation is to find more algorithms with advantage in comparison to classical devices. And a second question, which goes along with finding these instances, is to understand from what this advantage comes. So we believe it's quantum mechanics because we use the quantum Turing machine, but more specifically, various quantum phenomena were pointed out as the reason for quantum advantage. But all of them were shown to be necessary conditions, but not sufficient conditions. So we cannot build a quantum algorithm having superposition, entanglement, contextuality, and bigger negativity, and at the end guarantee that it has advantage. And one thing that we notice and we observe is that all of them describe something which has no temporal structure. They are mainly phenomena about the quantum state, and they don't describe really what we have in quantum algorithms, which is a process which processes information until at a certain point we have our output or goal. And so to study the temporal structure, there's a very interesting class of quantum circuits, which is the instantaneous quantum polynomial circuits. They're interesting because they have no temporal structure for the operations. That means that all gates commute between each other. And in this scenario, quantum advantage exists in the form of sampling. So like boson sampling, the distribution that we get at the end is very difficult to simulate classically, so it's exponentially difficult. However, we don't know anything useful that we can do with these distributions. They serve as an instance to show that a quantum advantage exists, but not to solve something computationally useful. And this motivated us to look at the measurement-based quantum computation model because it has a very specific way of computing by performing measurements on a very entangled quantum state, a highly entangled quantum state. And more precisely, the measurements in a measurement pattern depend on previous measurement outcomes. And so there's a very natural structure to define what has to be done previous to something else. And generally in literature, this is defined as the flow at the G flow. So in our case, we wanted to start from the most simple case. So the case where we don't have adaptivity. So all the measurements do not depend on previous measurement outcomes. So all of them commute, and we can perform them in any order as we want. And this setting is again the same setting as the IQP circuits. We can find quantum advantage by selecting a specific quantum state and measuring in a specific set of observables. And the distribution will be classical, difficult to simulate. However, we want to understand if in this setting we can solve something useful, for example, compute decision problems, which is the most general problems that we can define. And what's very interesting is that this scenario is also equal to the setting where we have non-local games. So we are doing measurements on a correlated quantum state, and we are asking between some correlations of the measurement outcomes, like a Bell and Bell inequality. And actually, what will happen is that each Boolean function that we try to compute is exactly equivalent to one Bell inequality. And so looking to what was known about this model is that any Boolean function can be computed deterministically if you have given access to a GHZ state. The problem is that this GHZ state can be of exponential size. And more precisely, this was bounded by the degree of the Boolean function, which is a very general measure that we have for Boolean functions. And so it scales very badly with the degree. And more precisely, or more simply to understand, is that very general functions that we use as the end, the exact, the majority scale very badly. So they are not efficient without a temporal structure. Then there was a problem in between, which we tried to solve, which is asking at least if Boolean functions with a constant degree could be computed efficiently on this model. So if they don't need a temporal structure. And so we selected this family of symmetric functions. They are called complete symmetric functions. And what's interesting is that there's one for each degree. So we can study each degree by itself. And they are also very interesting because they form a universal basis for all symmetric functions. So for example, building up again the majority function. And so for this ones, we could reduce the upper bound. So we found GHZ states of smaller size which compute them. And we conjecture also a lower bound for them, which now allows us to compare with the classical scenario. And also we upper bounded the Clifford hierarchy of the measurement operators. So the measurement operators could be not simply poly measurements. It could be more complex, and we have to build them from a set of gates. So defining the complexity of the measurement operator is also necessary. And now defining the conjecture more precisely, we conjecture that the number of qubits needed in the GHZ state scales with a polynomial whose exponent is half of the degree of the function. So the next task, after defining the size of the quantum state we need and the type of measurement operators we need to compute the Boolean functions, we wanted to go from this abstract description to circuits. And so we defined a universal gate set. And this was the Clifford plus T gate set. And then we've defined the whole circuit that we need. So the circuit which builds the quantum state, the linear processing of the input string, creating the measurement operators, and then the post-processing. And then we get the characterization of circuits or algorithms. So we have a width, we have a depth, and we can count the number of gates. And in this scenario, we found a quantum advantage. It happens for the first complete symmetric function, so the one of degree 2. And for this one, we could show that any circuit that can be built with this rule, so we can copy at the beginning the input string as many times as we want, and then we process it with the general universal gate. And we could show that in the quantum setting, we can have advantage of this logarithmic term in comparison to the classical case. And that's very interesting because it doesn't depend on oracles. It's a white box separation. The only restriction to be universal separation would be to allow the copy operation in any point of the circuit. That's the only restriction that we are imposing. So as conclusions, we have seen that measurement-based quantum computation without the temporal structure can have advantage, at least for one specific Boolean function, which is the one of degree 2. The other ones we ruled out with the conjecture, which we need still to prove to be very precise. What's interesting is that the case where we found advantage, when we look at a non-local game equivalent to it, we have the generalized Mermin inequalities. So the Bell inequality correlates to a non-local game where we can win with an exponential advantage. But when we play the game locally with circuits, we have only a logarithmic advantage. And that's a very interesting observation that we made. Also, there's another hierarchy of quantum correlations now that you can look. Normally, we say that something is quantum if it violates a Bell inequality, and it's classical if it's not. However, now we can ask a quantum state how strong the correlations are by trying to compute more complex functions on it with higher degree, now that we know that it's something more difficult to do. And generally, we see that without a temporal structure, we are not very efficient in computing decision problems. As ideas for future work, we want now to introduce additivity in, for example, one adaptive layer and see how much computation we get from it, how much computational power we obtain. We will try to study the same problem, but now for relation problems, which have been shown to be prone to quantum advantage. So there are this results showing that in constant quantum depth, there are some relation problems that can be computed, while a classical device cannot do it in constant depth. And we could propose some experiments on GHZ states, which have previously shown possible. And now we have more functions that we could try to implement. And thank you for your attention. If you want to have a look, you only need to have scan the QR code.
We have questions.
Someone is having a question. So your Boolean functions are like with output zeros and ones.
Yeah, exactly.
So have you thought about having multiple outputs? Then you could maybe, is there any?
Yeah, that's the relation problems. That's what we wanted to look in the next step.
I think, like, for example, then you could do like counting problems.
Exactly.
Or max cut.
Yeah, that's the next step we want to look at. Yeah, we started to restrict to decision problems because they have also this connection to, they are simpler and they have the connection to the non-local games, which was also a starting point for us.
So may I ask a second question?
Yeah.
So it's just because there was a lot of information. So if I understand it, at the beginning you had, like, I prepare a state and I can only input a string of X.
Yeah.
And then I get some output. Then the second model, you are allowed to kind of settings of circuits. I mean, like small units of circuit you can implement depending on the.
It's in the setting of the measurement-based computation model. So it means that we can measure, and then we have more entangled qubits, which were entangled with the first ones that we measured. And now we can look at the measurement results and adapt the second layer of measurements. And so this model was shown to be universal, and we can go for the circuit model and back, and they are equivalent.
Every time you use a section of your.
Yeah, one layer of the circuit, for example. Yeah, exactly. That's why we went to the measurement-based computation model, because it's very specific. If one measurement is adaptive to another, we cannot perform this measurement previous to the other one. So we know that it has to be in the next layer.
Okay,
thank you for the interesting talk. I have a question which is more on the fundamental side of the thing. At the beginning, you mentioned that all those resources are basically just sufficient, necessary resources. And then may I ask what resource could be sufficient? What sufficiency would mean?
Okay, that's a very good question. I think there's no answer for that, because if we would know what is sufficient for quantum advantage, we would have the ingredient to build all algorithms with quantum advantage. So what's sufficient is that for each one of these quantum phenomena, there was someone which showed that if it's not there, we have no quantum advantage. It's classically easy to simulate this algorithm. So without contextuality, there's a paper showing exactly that. We need contextuality to have advantage. The same for entanglement. So if the state starts from single qubits, which are not entangled, and we don't use entangled gates, we can simulate it very easily with the Gottesman-Hill theorem. And each one of them was ruled out when it doesn't exist. So we know that we need them, but I think we need something which describes processes. That's mainly about quantum states. And we need to define what is very specifically a quantum process, which could not be done classically.
Thank you.
That means the campfire will never end.
Sorry, actually, in contextuality, there are some works trying to introduce the idea of time. And so they are really trying to get to this.
And first comment and another question I have before. So, I mean, these, of course,